multi-robot teams. In particular, our objectives here are to look at kind of scenarios which have like a moderate level of interdependence, of coupling. So we're interested in domains in which robots need to work together to achieve a common goal, but they might not need to have very tight cooperation and coordination. For instance, domains like in which two robots need to carry a table together might not fit the specification. Furthermore, since we're interested in like bigger teams, we want actually scalable models, which is quite an issue in the multi-agent POMDP world. And furthermore, we want to be able to exploit communication between robots. We'll get to that in a minute. In the paper, we actually use two case studies. One is a cooperative target tracking example, picture of which you see on the right, in which multiple robots need to localize and track another robot, which is the target, and it's moving around. In the paper, there's also another simulation study on environmental monitoring by a number of UAVs. And because of the shortness of this talk, we'll only look at the first one. Okay, so multi-robot cooperation is quite useful in many applications, which is why we're looking at these kind of problems. For instance, could have multiple robots doing surveillance, doing tracking, or rescue robotics. And a key feature of many of these domains is that they're quite uncertain. For instance, in the tracking example, you might not know where exactly the target that you want to track, so you need to first localize it before you can track it. And there might also be uncertainty in the way your actuators affect the world. So POMDP techniques excel at dealing with these kinds of uncertainty. But if you look at the literature, existing models do not really suffice for addressing the kind of multi-robot problems we want to look at. And we'll get into this in a moment. And furthermore, there's a lack of scalability. And what we focus on here mainly is scaling in the number of robots, not so much in the tasks themselves. Okay, so what are the main contributions of the journal paper? Well, what we try to do is we try to emulate a centralized multi-agent POMDP. So multi-agent POMDP is a model in which each agent, each robot, shares their observations with each other. And that way you can compute a joint belief and use a single agent POMDP solver basically to solve that. What we want to do is we want to emulate such a multi-agent POMDP by combining single robot roles. So we split up the joint task in single task and try to compose those in a smart way. And we use a decentralized task auction to actually distribute these tasks among the robots. And they will be updated on the fly. These task auctions are quite popular in the multi-robot community, but we have a bit more of a theoretical backing for them. Furthermore, how do we exploit communication? Well, in a normal multi-agent POMDP, everybody shares their observations, waits for all the observations to come in, and then updates the belief and takes a new action. That's not really easy to do if you have a real robot team where there's like noisy communication might be delayed, etc. So we employ a decentralized data fusion filter to actually sort of maintain a joint belief in a decentralized way. This sort of decouples decision making in the belief update, which has benefits but also some disadvantages. But the good thing here is that we actually be able to exploit communication that is present in real robotic platforms. So we don't really make very unrealistic assumptions regarding the communication channels. So what our decentralized approach will provide in the end is a scalable a model that scales well with the number of robots, and that's quite robust under communication failures. So the system does not break down if some packet gets lost. Okay, to give you some more context, I'll try to review a bit the literature, multi-agent planning under uncertainty, different kinds of models. And to make this specifically focused for these multi-robot problems that we're looking at, I'm looking at two axes here. So on the y-axis, you have communication. So basically, do these robots communicate? Do the agents communicate? And basically, what's the quality of the communication channel? So none means that there are no messages being exchanged, and perfect means that communication is instantaneous and there's no noise, etc. On the x-axis, we're looking at the interdependence between the task of the agents. So if there's low, we assume there's very little interdependence, so they're very much not really coupled, while high means we're looking at tightly coupled coordination problems. So let's try to look at some models you could find in the literature and put them in this figure. So if we look at the bottom left corner, we could look at what I would call independent POMDPs. So basically this means you have a multi-robot task. You capture the task of each robot as a single agent POMDP. You solve it. You put all the robots together in the environment. You let them loose, and they execute the task. This might work actually quite well if you have like a task like a number of vacuum cleaners that are cleaning a building together. But the level of coordination that you could get here is actually very low. The good thing about this, though, is that each of these POMDPs is a single agent POMDP. So we've seen quite some progress in how to solve them. So these are, let's say, relatively easy to solve. So if you look at the bottom right corner, we have the decentralized POMDP, which is like the sort of the gold standard in this kind of multi-agent POMDP models. It only reasons about local information, the local observations. That's the only ones it considers. But in the back of its head, it's reasoning about all the other possible observations and actions that other agents could have taken in the meanwhile. This leads to a very high level of coordination. It's a very tightly coordinated model. But there's no real information sharing going on there. So that's not really what we would want. Plus, they are actually extremely hard to solve optimally. So if we would want to add communication to these kind of models, we end up in the top right corner, where we have the multi-agent POMDP that I already briefly mentioned. So the multi-agent POMDP has a high level of coordination as well. It exploits communication because agents share their observations. The problem is, though, that it actually requires perfect information sharing. So if we're a team of robots and one packet gets lost, the other robots do not know what to do. Basically, the assumption is that the packet arrives immediately, and if it's not there, the system breaks down. So on the other hand, these are also still quite hard to solve. Now they are single agent models, but the problem is exponentially sized. There are some models in between here, DEC POMDPs with communication, still high level of coordination, but they're still quite hard to solve. So what we want is what we propose here is something in the sweet spot in the middle. So we want to auction individual POMDP models, but try to actually coordinate them through this decentralized data fusion filter. So this makes them share information in an asynchronous way. So this is quite robust to delayed communication, etc. And since all these models are still individual POMDPs, are quite easy to solve. The downside is here that you need to have a domain which is suitable. You need to be able to do this sort of decomposition. Okay, so how does the decentralized data fusion filter work? Well, we have this, so we track a joint belief using this. Each robot, we assume, can estimate locally a local belief and then share this information. And then the centralized estimation would consider information from the whole team, basically reason about joint action, joint observations. And the nice thing here is that if you do the decentralized fusion, if you let it converge, it will actually converge to the centralized solution. In practice, there might be some discrepancies due to the fact that it's a quite dynamic system. And these models are quite robust against delayed communication. So what about our distributed POMDP model? So we assume basically that the original problem can be modeled with a set of roles, let's say non-overlapping single agent behaviors. Then each of them can be modeled with a single agent POMDP. In our experiments, we actually assume that they all have the same reward function, but that's not necessarily true. And then we emulate the original multi-agent POMDP by having this common belief signal using the decentralized data fusion filter and compute policies for the single agent roles at which we allocate online using decentralized auctions. Obviously, this will lead to a suboptimal solution since we're not reasoning about the joint observation and joint actions, but this is quite scalable and flexible. Like it's easy to add a robot or remove one. So how do these task auctions work? So basically, for each task, each role, in our case, you need to have a bit function that tells you, okay, how fit I am for executing a particular task given my local information. And in the robotics community, these are typically defined ad hoc and often quite heuristic. So a couple of years ago, we had a paper at ICAPS where we show how if you define tasks in the decision theoretic framework, like POMDPs, if you solve each such task, then what you get is a value function, for instance. The value function tells you not only how to execute this task, but also what to bid, because it basically estimates the value you get. So we can use these bids to run a a decentralized auction, where we basically solve local assignment problems. Okay, to get to one of the experiments that I promised you, so we're looking at the cooperative tracking application. We are, in the auction POMDP case, we auction 4 different behaviors. We try to approach the target from different directions, because that will basically improve the localization of the target. And the target is moving, and so we have the decentralized auction and the decentralized belief state going on. And what I will show you is a video comparing these auction POMDPs versus independent POMDPs. Note that the independent POMDPs basically still share information using decentralized belief state, because if they wouldn't, the behavior would be very silly. Basically, everybody's just looking for the target on its own.
Here, I'll do the video you do.
Okay. So my dear assistant Leslie will switch to the video. So what you'll see here is on the top are will be.
Say something interesting.
Okay, and on top you will see on the left, here on the left you will see the actual video of the robots moving in the basement of the University of Seville. And the top there will be here the auction POMDPs for our approach, and the bottom will be the independent POMDPs, which are basically not coordinating that well. And on the right here you will see the the control is dying. Okay, well. You can see the basically the control panel of the operator, seeing the 3 robots track the target in green. No?
No, like dead.
Dead?
Dead. I've never seen this happen before.
I'm.
So, do you need a laptop?
Yeah.
Yes, we do apparently need a laptop. I don't know, something, it's kind of like a non-Mac.
It's just a PDF, so I think it should be fine. We'll try not to show the video.
We'll just read it right from the drive.
All right, well, while we're getting this video set up, why don't I take questions for the speaker right now?
Which file?
Does anybody have any questions about what he's been talking about so far?
There's a folder called ICAPS 2014.
Here?
We should try the video, see if it works.
Of course it's going to work.
Okay, great. So, yeah, basically this is exactly what I was telling you. So this is a target here in both cases. And what you will see is that the robot on the bottom, because basically they're executing the same policy, using the same decentralized belief state, they all try to do more or less the same thing. So they get a little bit stuck in the corner here, which is the corner over there. So you can't see them at the moment. This video is sped up, as you can obviously see. The ones on the top, actually, since they are trying to approach the target from different directions, the behavior is much better. And they will, first of all, they don't get stuck, they don't obstruct each other. And also, as you can see in the paper, the final localization accuracy is much better if you do like a coordinated approach versus the independent. Okay, that's it.
Okay, let's.
Wait, I have 2 more slides.
You have time for questions, maybe 1 or 2 questions.
Okay.
If you want to quickly do some conclusions, like 30 seconds.
30 seconds should be right.
Okay.
Oh yeah.
There's
Well,
buttons right here.
okay, great. So basically, I just want to show you that this actually scales quite well in the number of robots. Since we don't have this many robots, these are actually simulated robots. But you can see that the reward per robot goes up as you get more robots, and the entropy in the final estimate of the target goes down. And so the main feature here is that the roll assignment is the only thing that scales with the number of robots, and these are milliseconds. So you can see this goes quite well until we get like 20 robots. It's nicely polynomial. And so our conclusions are that we basically looked at multi-agent planning in robotic environment. We did a little review of existing models, and so it's hard, you have to look at what's optimal and what's applicable. And so the conclusions were that we have a nice scalable approach for a class of multi-robot POMDPs, where we actually exploit communication, and we actually demonstrated this in a robot. So future work would be one major point is a precise characterization of our problem class, like what kind of problems we can solve well with this, with our approach, and perhaps ways to actually come up with these behaviors and factor models automatically. Thanks.
So I apologize to everybody for the technical difficulties. It's very interesting work. Matthijs, I'm sure that anybody that has a question will approach you offline to answer that. I guess one kind of interesting cross-cultural thing about roboticists here at ICAPS is we all have movies and they all run in different formats on different computers, so it's very hard for us to consolidate onto a single computer just for future conferences. Anyhow, next we have Leslie Kibling, and she will be talking to us about integrated task and motion planning.